Ah, well, it turns out we don't need the mic, because you could hear me because I'm just that loud. Yeah, being a loud, obnoxious person pays off sometimes. Hi. So, yeah, we'll get started in a minute here. I guess folks are still trickling in. How's everyone's day been so far? Great talks, eh? Awesome. Awesome. So since we're a couple minutes past our scheduled start date, let me get things rolling here. Hello. I'm Anjana Vakil. You can find me on Twitter at my name, because I'm not good at making clever internet handles. And I am here to talk to you about immutable data structures for functional programming in JavaScript. So we're going to talk a little bit about immutable data and why it's cool. We're going to talk a little bit, but very, very briefly, about functional programming and why it's cool, but more about the immutable data. But first, I just want to tell you a little bit about myself and some of the awesome communities that I'm really lucky to be a part of. So yeah, as I said, my name is Anjana. I live in San Francisco, and I work at Mapbox, where I am engineering, learning, and development lead. Anybody know Mapbox or use Mapbox? Yeah, a couple hands. All right, awesome. So Mapbox, if you haven't heard of us, we make a location data platform for developers. So we basically make a lot of tools and building blocks to help developers like us put really beautiful, customized, interactive, and basically immersive location experiences in your apps, whether that be on the web, on mobile, even on things like Unity, AR. So if you are interested in maps or location experiences, or you work on things like that, and you want to talk about it afterwards, please come talk to me. We are not going to talk about any of that stuff in my talk today. But I did want to tell you also about a couple other affiliations I have, because some of these groups are really fabulous, and I wouldn't be standing here in front of you today had I not met some of these people. One community that I absolutely love is called the Recurse Center. Recurse, like recursion. It's a programming retreat in New York City. Programming retreat, what's that? It's kind of like a writer's retreat, but for coders. So it's a place where you can go for 6 weeks or 3 months and be surrounded by other people, and all of you are just there to get better at programming, whatever that means to you. So it's self-directed, there are no classes, it's unstructured, but it's an amazing place, and it's really just such a great group of people. And it's while I was at the Recurse Center a few years ago that I got interested in functional programming and learned about these immutable data structures that I'm going to tell you about today. So if you're interested in doing really fun stuff with really fun people and getting better at programming, go check out recurse.com. Another community that I always love to talk about, because I, again, would not be standing here had I not found them, is a program called Outreachy. Outreachy is an initiative to get more women and underrepresented minorities involved in open source by offering paid, remote, 3-month internships at organizations like Mozilla to work on open source projects. These internships are remote and they are global. They're open to people all over the world. So if you or someone you know is a woman or underrepresented minority in tech and is looking to get a foot in the door in open source, check out outreachy.org. And if you work on an open source project, or your company works on open source projects and might be interested in sponsoring an intern, also check out outreachy.org. Got all the information there. Really, really great initiative. So I spent some time at Mozilla through Outreachy a few years back, and I'm still involved in Mozilla as a member of the Moz Tech Speakers. So you might have seen folks running around conferences around the world with this blue and yellow heart logo. We are basically volunteer Mozilla community members who love to go out and talk about open web technologies at events like this and all over the world. And so if you ever see us around, please come out and say hi. And it's also a really great way to get some training and support in public speaking skills and get involved with Mozilla. I believe we just had an application round. I'm not sure if the applications are still open, but there'll be another round. So check out Mozilla Tech Speakers. Okay, all right. Plug section of the talk over. Got to get it out of the way. Recurse.com, outreachy.org, MozTech speakers. Okay, done. So now we can really begin things. So, as I said, I'm here to talk to you about immutable data. And the reason that I want to talk to you about immutable data is because it's really useful for functional programming. Now, I happen to think that functional programming rocks. Anybody agree with me? Yeah? All right. We got some functional fans in the house. So I'm not going to spend too much time talking about what functional programming is or why it's cool. We'll look in depth at immutability and how it relates. But basically, in a nutshell, functional programming is a paradigm, a way of understanding and creating our code so that our programs are made up of pure functions, where a pure function is a function that looks at its input, whatever arguments you pass in, does something with that information and only that information. It doesn't look at anything else in the world, does some computation, and then returns its output. And that's all it does. Takes data in and returns data out. It does not do what are called side effects, which is changing anything else in the world or doing anything else besides returning a value. So this could be something like writing to a database or printing something to the console or changing some global state somewhere. We don't do any of that in a pure function. So we can think of pure functions really as these kind of data transformers where you just take data in, you do something with it, and then you return data out. And one of the things that goes hand in hand with using pure functions is avoiding mutable state. So avoiding values that change in place over time. Basically, if we avoid mutability, we can constrain ourselves to a safer way of programming. And this is one of the things that goes hand in hand with functional programming. And that's because immutability, the idea of fixing values in place and then never changing them, also rocks. And that's what this talk is going to be about, is why immutability rocks and how we can create data structures and work with functional data structures that make immutability really efficient. So, okay, imagine a land where mutation reigns. That's pretty much our regular old everyday programming. Like in JavaScript, we have mutable objects. We have objects that we can change in place. So in that world, our current world, if I have an array, and it's called foo, and it's got some integers, a 0, and I'm like already bored, right? Because why is every computer science programming example named something super boring, like foo, and it just has a bunch of boring integers in it? Like, why? Can't we have something cuter and more fun, like a zoo, with some emoji in it? Let's do that. Okay, so we've got an array. It's called zoo. It's got some animals. They're real cute. And since this is a mutable array, if I want to change something, like maybe I'm kind of bored with my koala there at index 1. I want something a little more exotic, like an alien. It's more exotic. Since this is a mutable array, if I want to change my original zoo so that it has an alien in it, all I have to do is just swap them out. I can remove the koala, put in an alien, change it in place. I don't have to touch anything else. Pretty convenient if I want to update my data. However, my coworker was working with the zoo and was writing some code that depended on all of the zoo animals being terrestrial Earth animals, and was not expecting an alien, and now my coworker is super mad at me, and she's like, who did this? Who changed my data out from underneath me? Like, why? Like, what happened? I had a zoo, I thought I could depend on it, and somebody changed it out from underneath me. Not cool. So now I'm in trouble, my coworker's having a bad day, I'm having a bad day, sad face, right? Okay, so this is the problem. When we use mutable data, we can change values in place in ways that are unexpected. And so if we want to manage that and make our lives possible as developers, we have to add a lot of overhead to manage like who is allowed to change the data, how and when, and validate and make sure that like all the animals are from the earth before we process anything, and yada, yada, yada. So it's a lot of overhead, it's a lot of headaches to have to manage all of that. And because we are humans and we make mistakes, we're probably not going to be able to manage everything perfectly. We're probably going to miss some things, and we're going to have bugs in our code. So this is the idea, is that mutability is dangerous. And on a good day, it'll give you a headache. On a bad day, it'll break everything. Right? So this is not ideal. So now, I'm going to say something that totally disagrees with my feelings about the comic book characters, the X-Men. I love them. I love Professor X. But Professor X, you're wrong. Mutation has to be stopped. No mutation. Great for the comics, not good for code. So imagine that we journeyed to a different land. The land of immutable data. Da, da, da. Okay. So immutable data, meaning once we've created this data, we can never change it. It cannot be changed in place. Once it's there, it's like carved in stone. It's not going anywhere. That's how it's going to be from now on. So now we're in the land of immutability. I have an array called zoo. But if I want to update my koala to make it an alien, I can't change zoo. It's there. I created it, and it is immutable, so it's always going to be there. It's always going to be these exact animals. So if I want a new array that has an alien in it, what I'd have to do is create another array. I'll call it new, because I'm that creative. And in this new array, I can put my alien in index 1, instead of the koala. And then what I have to do is go through and copy all of the other values, all of my other animals. Copy them into the array. OK, so now we've got immutable data, which solves some of our problems of before. My coworker, for example, is having a good day because I didn't change the zoo that she's working with. I just created a new thing that I'm working with. So I didn't mess up what she's doing. So she's fine. She's like, yeah, my zoo is just how I wanted it. Great. But this code now is not super performant because I wanted to change one thing in my array, and I had to create a whole new array, so double the size, double the amount of memory, and I had to sit there and copy through every value into the new array. So I had to spend a lot of time copying when I really just wanted to change one thing. So now we've got code that runs slow like a turtle, takes up a lot of space like a big old whale. Not fun. Not the most fun. So immutability is great, but if we handle immutability naively by copying, which is valid, we have the problem that we're wasting time and space. By the way, folks, there's plenty of seats. Come on in. Don't worry about it. It's a party. Yeah. OK, no pressure, but, you know. Anyway. All right, so there must be a better way, right? There's got to be a better way to work with this data. And that's where we need a hero to come on the stage. Sound effects. Persistent data structures are that hero. What's a persistent data structure? Well, let me tell you. Master of time and space. It is a way of handling immutable data that allows us to keep old versions around. Our old versions never change. They stay there forever. Well, for a long time. And new versions are much more efficient to create than via our naive copying approach. So we're going to talk about persistent data structures for the rest of the talk. But just a note on terminology before we actually look at what these things are. Persistent data structures and immutable data structures are sometimes used interchangeably. They technically refer to different things. So immutable data structures are just any data structures that cannot be changed. Persistent data structures refer to this feature where the old versions hang around. And I'm not going to go into the nitty-gritty of like different types of persistence. There are a few different levels of it. You can look it up. You have computers and the internet. You can figure it out. But we're going to talk about the big picture idea, the insight behind these, which I think is really cool. So for the rest of this talk, we're going to be talking about persistent immutable data structures. And we'll just think of that as one concept, even though there is a little bit of nuance that we won't go into there. Cool? Cool. All right. So persistent data structures. I have told you that they are a superhero, that they are masters of time and space, but what is the source of their power? Well, it's two really simple, really beautiful things, I think. Trees and sharing. Oh. Isn't that sweet? Sharing is a superpower in computers, turns out. Also in life. All right, so how does it, what am I talking about? How are trees and sharing superpowers? What? So, in a more efficient way of dealing with immutability, instead of taking my original immutable array, I'm going to turn it into a tree. And we're going to see how that helps me more efficiently create new copies when I need to change something. So to turn this zoo array into a tree, what I'm going to do is split it up into nodes where these nodes are going to become the leaves of the tree, and they're going to hold our values, our animals in this case. Now, I could split it up so that each animal is its own node, but then they might get lonely. So let's put them with a buddy. OK, so I've split up my array into nodes of size 2. So we've got 2 values in each node. And what I'm going to do to unite these into a single data structure is form a tree by taking more small nodes of size 2 and linking up our leaf nodes, our value nodes. So now I've got pairs of nodes of 2. And then I'm going to take more nodes and link up the pair nodes, and so on and so forth until I reach a root that is going to represent the entire structure. So this is going to be a tree equivalent of the array that I had before. Now, you're probably thinking like, all right, that seems unnecessarily complex, like we just had an array before, that's all we need. Aha, but this has some advantages. So, what happens when we want to update something? As we saw before, in just a simple array, if I have an immutable array and I want to update one thing, I have to allocate an entire new array of the same size and copy everything over. Let's see what happens in the persistent data structure, the tree version. So in this case, if I want to change one thing, let's say I want to change my koala and have it be an alien in that slot instead, what I need to copy is just that node. Just the node, the leaf node, that contains the value that I want to update. So in this case, the node 0, 1. I'm going to create a new node, put in my alien, and then copy over anything else in that node. So I still have to copy a little bit of extra data that I didn't want to change. But in this case, I only have to copy one extra value, the monkey, that I am not changing, as opposed to copying the whole rest of the array. So I copy that, I make a new version of my leaf node that I want to update. Now, what I do is I create a new intermediate node that links that new leaf node with whatever its pair had been in the original tree. So I'm going to link it up with the node 2, 3. And then I'm going to take a new node and link that intermediate node up with whatever its pair was, and so on and so forth, up the tree until I get to the root. So what I've done here is copy every node on the path from the leaf, the value that I wanted to update, to the root of the tree. This is, unsurprisingly, called path copying. I copied the path. Some jargon. We gotta throw in the nerdy jargon. All right. Now this is where the cool part comes in. The tree structure and the fact that my new node is now linked to the old nodes in the tree means that I get to share a large part of the structure of the original tree with the new one. This is called, unsurprisingly, structural sharing. So, what I've got now is that most of the nodes in the tree are the same. I haven't had to touch them. They're the exact same nodes. The only things I had to change were the leaf node and anything between the leaf and the root, that path. Cool? So, this is great because now, instead of having to copy everything else in the array, all those other animals that I didn't want to update, I can reuse them. That means that with just some trees and some structural sharing, I'm able to turn a copying operation that was really slow and took up a lot of space into something that's much faster, like a racehorse, and takes up much less space because I'm able to reuse so much of it. So it's like a little shrimpy guy. Amazing, right? Who knew there were so many different animal emoji? I did. No. Okay, so now you might be thinking, all right, fine. So we know how to create a persistent data structure, a tree here, and we know how to update something in it, but like, how do we get something out? How do I access one of my values? In our original array, it's just a simple indexing operation. I just index into the array and I get out my animal. How does this work in this weird tree situation? So this is where our tree reveals a secret identity it has been hiding all along. It turns out that this whole time, our tree has actually been a TRIE. What? It's a tree. It's a TRIE. So TRIE is often pronounced try to distinguish it from TREE, tree, but it could also be pronounced tree because it comes from the word retrieval. So a TRIE, TRIE, is just a particular type of tree where the leaves hold values, the values that you're trying to deal with, and the paths from the root to the leaves represent keys with which those values are associated. So it's just a special type of tree. Call it a TRIE. You could also call it a tree, but that's confusing, so I'm going to call it a TRIE. I'm going to try to remember to call it a tree. No, I'm going to try to remember to call it a TRIE and not a tree, and this is why programming is hard. Okay. So, tries are often used for things like a dictionary type application where, let's say you needed to associate words with values. So maybe I want to associate the names of animals with their respective emoji. A trie can be used like this, where basically I start with a root, and from the root, I create a separate branch for every possible first letter of any of the animal names that I have in my animal dictionary. So I might have A branch, and a B branch, and a C branch, and so on and so forth. And then, from each of those branches, I create a branch for any possible second letter. So if I have ant and ape, from the A branch, I'm going to create an N and a P branch, and so on and so forth until I reach the end of the word, which is the leaf node that holds my value. And so then the way we can access things is by descending the tree. If I want to look up, find the ape emoji, I can descend the tree letter by letter. So I start at the root, I go to A branch, then I follow the P branch, that gets me to AP, then I follow the E branch, that gets me to APE, ape, and I get my emoji out. So this is often also called a prefix tree, because at each level of the tree, we have a prefix of the words that are, the keys that are holding our values here. Just another name. Now, okay, you're probably thinking like, all right, but we don't have words associated. We're trying to make an array. We need integer, we need indices for these values. So how does that work? How is this applicable? Well, what if we took our index and we converted it into binary, and we treated that binary number as a word where we could step through bit by bit or letter by letter until we get to the full word, the full index. Let's take a look at what that could look like. So I've taken the same tree that we had before and I've just annotated it. We always had 2 branches at each level. Now I'm just going to name them 0 and 1. Fair? Okay, hopefully it's fair. Same tree. And then I've just annotated the indices at the bottom with their binary equivalents. So now instead of 0, we've got 0, 0, 0. Instead of 2, we've got 0, 1, 0, etc. All right, so now if I want to look up what is the animal that I have at index 5, let's say, I can convert that number to binary. So I get 101. And then I'm going to step through from the root 1 bit at a time. So from the root, I'm going to go to the 1 branch, which is the right-hand side. Then I'm going to go to 0, which is the left-hand side. Then I'm going to go to 1, which is the right-hand side. And I get out my ape, my gorilla, which just happens to be at index 5. Cool? All right, so this is the insight here, is that if we can treat these indices as sort of like words, and we can look at prefixes of those words and descend the tree that way, then we're easily able to look up a value in our array, in our persistent array-like thing. So what is this thing? Is it a bird? Is it a plane? No, it's a bitmap vector trie. What? I don't know. It's just jargon. It doesn't matter. You don't need to know this. But if you're curious and you want to look it up, you want to Google something, you can Google that. So bitmapped because we are looking at one bit or one portion of the binary index at a time. Vector is just a word for an array-ish thing. And we already talked about tries and how cool they are and how hard they are to pronounce. OK, so while we're talking about nerdy jargon stuff, let's talk about time complexity. So in our regular immutable array that we saw at the beginning, it's an array, so lookups are real fast. Lookups are constant time. We just grab the index and we go. But as we saw, updating an immutable array means copying the entire thing. So I have to go through every single value. So that's a linear operation. Whereas in my bitmap vector trie, updates are now quite a bit faster because instead of copying everything, we only had to copy the path from the root to the leaf, which is going to be a logarithmic operation. So this is going to be logarithmic time complexity. That's cool, because that's faster for updates. However, lookups are also logarithmic, because we had to step through every level of the tree as well. So lookups are now quite a bit slower than in our regular immutable arrays, right? And don't worry about the O notation. This is just, let's think about the ideas. And the problem is, as our arrays get bigger and bigger, like if we have thousands and thousands, tens of thousands of things in our array, these binary indices are going to start getting pretty long. So like if I want to look, if I have 20,000 things in my array and I want to access item at index 18,977, say, I would get this long 15-digit binary equivalent of 18,977. I bet you all knew in your heads what 18,977 was in binary, right? Yeah, totally. Me too. Anyway, I'm going to have to step through that. Go to the 1, and then the 0, and then the 0, and then the 1, and it's like, oh my god, that's going to take a million years, right? So as our arrays get really, really big, logarithmic time complexity is still not amazing. However, who said that we needed only 2 branches at every node in our tree? All the trees that I've been showing you only have 2 branches per node, two options per node, right? That's because they fit on slides. So nobody said that two-way branching is the best way to go here. We could pick an arbitrary number of branches for every node in our tree, or arbitrary size for every node. And then our leaves would have that many animals in them. We could pick 4, or 8, or 32, or 64, or whatever we want. And so instead of having, as all the examples that we've seen before, where we just have 1 bit of information per level, because we have a choice of 0 or 1 for each level, we could pick an arbitrary number and have however many bits we want per level of the tree. So folks have experimented with this, and they've found out that there is a sweet spot of about, there's a sweet spot in a trade-off that we have to make between the size of those nodes, the number of branches, the branching, the degree of our trees here, and the depth of the trees that we're going to create. So if we have fewer branches, like if we just have 0 and 1 as our options, then we do have that problem of deep trees, but our nodes are really small. So when I wanted to create that new version of my leaf node, I only had to copy 1 extraneous value. I only had to copy 1 extra thing, so that's cool. Whereas, if we wanted to have more branches, we would get a much shallower tree, because we'd be able to represent more bits of information for each level. However, the trade-off would be that the nodes are larger. So, and remember, when I created the updated tree, I had to copy everything else in the node. And so as those nodes get larger, that's also going to cost me time and space. So folks have experimented with this trade-off, and they've found that there's a sweet spot at 32. 32 is the optimum size. It's kind of the nice trade-off. So they, capital T, say. I haven't tested it myself. You can play around, but I trust them. They've done research. There's graphs, people. There's graphs. Anyway, so 32 values per node, meaning I have 32 possible branches at each intermediate node, and then I have 32 leaf values in my leaf nodes, meaning we're representing 5 bits of information for each level of the tree. So this means now, in my 15-digit, 18,977, instead of stepping through 1 digit at a time, I can step through in chunks of 5. I can step through 5 bits at a time, which means I only have to go through 3 levels of this tree to get to the 18,977th element, which is pretty cool. So now, we go back to our discussion that we were having before about the time complexity. And okay, yes, lookups and updates to these type of trees are logarithmic. They're trees. There's no way around it. However, the base of that logarithm we can make so big that this number is going to be, for all practical purposes, really small. So even if we have like 2 billion something things in our array, which is like, I think the largest number you can represent in JavaScript is 2 billion and odd change, and in many other systems. So the largest possible thing we could conceive of, the largest possible index we could conceive of, the log base 32 of that is something between 6 and 7. It's a small number. So that means, and people often say that this is technically logarithmic, but effectively constant time. Because no matter how big your array gets, you're gonna have like a small integer as the number here. So you'll often hear this called effective constant time or effectively constant time, meaning there's not gonna be a practical difference. Even though it's technically logarithmic, you're probably not gonna notice much of a difference between a constant time operation here. So that's good news, because now we get not only much faster updates, but also our lookups are not much slower. So basically we're just winning, just all day long. Okay, now, really quickly, we're going to talk about objects. So far we've just been talking about array-ishness, where we have index. We want an index associated with a value. What if we want a non-integer key, like a word, like ape, or some other arbitrary object that we want to be a key? Well, we can do that too. So let's say I wanted the first letter of the animal's name, like M for monkey, K for koala, etc., to be associated with the animal's emoji instead of a number, like an index. What I can do here is take those keys, those string keys, hash them to get some number, and then do the same thing that we did before. Now, this works because we're in the land of immutability. So everything that we have is immutable data. It means it's totally fine to hash. It's never going to change from out from under you. You're never going to be able to mutate the key here. So we can take, let's say I want to find the animal associated with key G. I can take some hashing function, and I have a really convenient one that gives me 5 for G, because slides. And again, I just convert it to binary, and then the same as before, I step through, and that is going to be that's going to get me to the animal, the value that's associated with the, in this case, string, but really arbitrary object key that I have. Cool? So this is I think it's pretty cool, because this means, and again, in the land of immutability, any object can be used as a key here, because we can hash whatever we want. So that's awesome. We have arbitrary keys. I don't know, kind of fun, probably useful, maybe. We'll find out. This whole thing is called a hash array mapped TRIE, or a HAMT, because that's fun to say. This is a thing you can Google if you want to learn more about it. It's a data structure pioneered by a guy named Phil Bagwell. There's a surprisingly approachable paper about them. And then implemented in functional languages like Clojure and Scala. And these type of data structures were really a huge leg up for functional programmers because it made it so much more practical, so much more efficient to do the type of functional programming that depends on immutable data. So it's a really cool thing, and the implementations of these are really awesome, and there's a lot of detail and optimizations that I have not gone into here because we're just talking big picture, but there's a lot of great resources on that, and I have some linked at the end of these slides, which I will tweet out later. So, hash array map trie, HAMT, fun times. To recap, mutability, headacheville, no fun, bugs, mad coworkers, not a good time. Immutability, ooh, spoilers. Immutability, rocks, super hard because it saves us from all of that. However, dealing with immutable data naively by copying, not amazing because it's really slow, it takes up a lot of space. Using trees with structural sharing, aka persistent data structures, gives us much faster and much more space efficient operations on this immutable data. So, huzzah! Yay. Okay, so hopefully by now I have convinced you that these are some pretty cool data structures. They're pretty fun. They have sharing as their superpower. That's just heartwarming. But okay, so far we've just been talking about like abstract, theoretical emoji structures on slides. How do we actually use them in JavaScript? Libraries. You do not have to go read Phil Bagwell's paper and go sit down and try to implement these data structures in JavaScript. You can, if you really wanna, but other people have done it. You can use their libraries. So there's a lot of options out there. There's a lot of great ones. I haven't used all of them, so there's plenty of options that we're not gonna talk about. But there's a couple that I like that I wanted to tell you about. So one is Immutable.js. Anybody worked with it? Couple hands, few hands. All right. So Immutable is from Facebook, created by Lee Byron at Facebook, part of the whole React party system. Anyway, it's cool. You can read a lot about it. Docs are good. Basically, the way we use it is it feels very much like JavaScript. It feels very much like just working with regular JavaScript-y objects. So the creation is a little bit weird. Like this is one way we can create a list. A list is a array-ish, vector-ish thing. We can do this immutable.list.of the stuff that I want to make a list of. And then that gives us some object A, which it looks different from a JavaScript array only in that it says the word list before it when you try to log it out. Otherwise, it feels pretty JavaScript-y, and it even has what looks like a method a.push, like array.push, but actually this is not updating the array A. What it's doing is returning a new copy with the updated value. So even though it feels like a little bit mutatey, it feels a little bit object-oriented in the API, you're actually returning a new value. So I'm going to capture that as A2, and then I can prove to myself that they're different by checking the size of A, yep, it's still 2, and getting out the third item in A2, yep, 3 is there. So we actually did create a new thing. And similarly with objects, the object-ish thing that you might use is called a map. And we can create that from a regular JavaScript object with keys and values. And then I could use the set method, it's really returning a new thing, to update that, create a new map called O2. And I can use the get method to prove to myself that O hasn't changed, even though it felt kind of like I changed it. I did not. So this to me feels a little bit weird in Immutable, that we have this like object-oriented API that feels very much like mutatey JavaScript. I personally, when I'm trying to get into the flow of functional programming, I like to work with just a functional API. But you know, your mileage may vary. Everyone has their own taste. So this is a great library. You can check it out, try it out, see if you like it. If you want a more functional API, a more functional way of working, one little library that I like is called Mori. Mori is is from the Clojure ecosystem, from the ClojureScript world. This is by the creator of ClojureScript, David Nolan. And it's basically a way to access the ClojureScript implementations of these data structures from native JavaScript, vanilla JavaScript, as it were. And so this feels a lot less like JavaScript. It feels a lot more like Clojure. Here, instead of having method calls like a.push, we have these Clojure-sounding functions like conj, which is just basically the function for appending something to the end of a vector. In this case, is the arrayish thing. And so here, when I create a new vector a, you can see it doesn't really look like JavaScript. Like, where are the commas? Like, what even happened to the commas? What is going on? It's because it looks like Clojure. And when I want to do something to that, instead of saying like a.push or a.conj in this case, I have to call it in a pure functional way. So that means I'm going to call mori.conj, this is just the pure function, pass in the vector that I want to change, and then the new value that I want to add on. So it's just a little bit different way of working with this data. Feels a bit more functional, but also a lot less like JavaScript, a lot more like Clojure. And again, we can prove to myself that these are two different objects, and they have totally different, they're independent. I didn't mutate anything. And similarly, just as Immutable has maps, Mori has hash maps. In this case, instead of a set method, we have an assoc function, like associate. I think of it that way. And so we can say, OK, assoc into the object O, at the key A, this value 3. And again, I can prove to myself that this created a new thing. So this is another option. Very different. Try it out. Personally, I like the functional API. You may not. There's a few other little differences. So Immutable.js is all JavaScript. As I said, Mori is more ClojureScript. It's ClojureScript under the hood, basically. We've got the object-oriented versus the more functional API. There's a few differences. Like Immutable is a little bit smaller, I think. Mori is a bit faster. Mori also hasn't really been updated in a few years. But then again, maybe that's because it works. I don't know. So there's a couple open tickets and whatnot. So I'm not sure how supported it is anymore. But it's if you're trying to wrap your head around this stuff, it's a great tool. And there's a lot of other options out there too. If you don't like either of these, you have many other choices. So you can Google around for persistent data structure libraries. Another one I'd recommend checking out is Seamless Immutable by Richard Feldman. And it's great because it has both a functional and an object-oriented API. So you can choose. So yeah. That is what I have to say about persistent data, immutable data in JavaScript. I hope you will go try it out. I hope you will go live long and just most of all, not mutate your data. Thank you so much. Thank you very much to DevReach for having me here. Thanks. I think I'm over time, so see you all in the hallway.